Hi guys, I'm back. Well, apparently the last upload had a little bit of a problem with the audio, so I'm redoing it. So we're working on chapter 25, cutting operations. Okay, so as always guys, if you have problems or questions, maybe I glossed over something that you don't really get, let me know. Text me, email me, put something up on our classroom so that we can work together guys. Okay, I'm here for you. All right, so we're going to talk about how cutting is done. And there's kind of pretty much two different ways we can do it. One, we have a manual cutting torch. Or two, we have what's called a track burner. And pretty much you set up the torch and it goes along these little rails and cuts from what you've set. Okay. Now, we need to understand how do we cut stuff? Okay, and when we really think about this, this is actually science and chemistry, and it's the coolest part of it. Really, what happens is we oxidize our material. But what is oxidization? Oxidization is rust. So what's happening is we're having this chemical reaction with the oxygen and the acetylene, or our fuel gas, and it creates a chemical reaction with our metal. Ultimately, we're oxidizing it or rusting it really quickly, and the heat is allowing us to cut through it. Pretty cool, right? Science! My favorite. Okie dokie. So a cutting torch is a little bit different than a regular welding torch. What's the difference? We have two differences. One, if you look right here, it has an oxygen lever. Okay. Now here's our oxygen and our acetylene. Okay. And then the other thing is the tip. Okay. The one in the middle, that is our cutting hole or our oxygen. Okay. And the other ones around it are the preheat holes. That looks like a little flower on the outside. Those are preheat holes. So when I ask, what do preheat holes do? They preheat. All right, so correct oxygen and acetylene pressures are necessary. We understand that tip size is dictated upon, what is it? Thickness of material. Okay, thickness of material also will dictate pressures because we need to have a specific tip size to make sure we're going to be able to cut through the particular material. Okay, notice our oxygen pressure goes up. So we're going to, on average, we're going to work with probably about 40 pounds of oxygen and maybe only 3 or 4, maybe even 5 pounds of acetylene. We don't need a whole lot of acetylene. We need more oxygen because we're oxidizing. All right. Oh, well, let's talk about this first. So let's talk about how do we cut. So the cool part is that I can kind of show you here. Yeah, kind of. So what happens is that we're going to turn our torch on. So just like we would with the welding torch, we're going to crack open the acetylene and light it. Okay. And we're going to get past the welding fairies, or the little parachutes that they call them, past the little smoke, and that's where our acetylene sits. Okay. And then we're going to turn on our oxygen, and we're going to set up a flame that is 1-to-1 or a neutral flame. That means that the inner cone is going to be rather small. And then when we push down the lever, okay, it'll shoot out a little bit of oxygen, okay? And that allows us to cut. So what's going to happen is we're going to leave our oxygen lever alone for a second and pretend this is our plate here. We're going to make our cut along here. So the first thing I'm going to do is I'm going to preheat my plate. I got to get it nice and warm, okay? I want to go back and forth. I want to get it just a little bit warm, a little bit red, so it'll be ready when I want to cut it, okay? Then I'm going to go over to this edge right here. And remember, I'm not touching my oxygen lever yet, okay? All right, and I'm going to sit here. I'm going to be, my flame's going to be halfway on my plate and halfway off my plate. And we're going to kind of sit it right here, move it just a tiny bit, maybe in a little circle, okay? And we're going to wait for it to get cherry red. And then all of a sudden it's going to have these little sparkles or little pops, okay? And that's when we hit the oxygen lever. Then we're going to hit the oxygen lever. All the way across. Now, how do we know that it's going through the metal? Well, we're going to see the sparks spitting through. We might have some slag or some dross. The flame will go through, and a lot of times you can also see through the other edge. Okay, but we want to make sure that it's cutting through. If it's not, we may need to slow down or even speed up. Okay. All right, now they're talking about piercing a hole in the steel. So we're going to kind of do it in the same kind of way. So what would happen is we're going to make sure we draw our circle first. Wherever we want the hole, we need to make sure we draw it first. Okay. So maybe we're going to have a little circle here. Okay. Now I'm going to heat it up just like the same way I would my plate, but I'm going to heat up my little circle. Okay. Circle, 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 circle. All right, and then in the center of my circle, I'm going to sit there for a second. I'm going to wait for it to get cherry, cherry, cherry hot. And when I get the sparkles and everything, I'm going to hit my oxygen lever. But at the same time that I hit my oxygen lever, I'm going to come up a little bit. And the reason is that when you hit that oxygen lever, you're going to kind of get like this splashback. Well, we don't want any of that splash of material to come into our tip. Okay. So usually, when we weld, we're probably about 1/8 to 1/4 of an inch off the plate. Because remember, if we're too close, we will starve it and it'll go out. And if it's too far away, it won't cut. So we have to have that happy medium. Okay. All right, and then when we make bigger holes or bigger shapes, we can use soapstone. Okay, soapstone is fine. I don't prefer soapstone when we're doing stuff like this, only because I ran into problems myself that I get my soapstone line, I turn around, I bump it, and I just smeared my line. Okay. I usually will use a scribe, something to scratch it with, or even a Sharpie because it doesn't rub off and it makes it a little bit easier. All right, to make a bevel cut, well, we're going to angle it to whatever angle that you would like the bevel cut to be. Now, if we're going to cut round stock, round solid piece, okay, we're going to start at a 90 and keep going all the way to 90 as we go all the way over. Pretty simple, okay? We don't have to turn it at all. Just keep it up and down and keep going. Oxygen and acetylene pressure, though, are different when we use cast iron. We want a little bit of a carburizing, okay? And if you notice, we have, well, really, what makes cast iron cast iron? Cast iron has a lot of carbon. Carbon makes it strong, but there's a payoff for being strong. It also can make it brittle. So when we do cast iron, we have to do a lot of preheating and a lot of post-heating so we don't get cracking. And then when we cut it, they say to cut it in a sawing motion. So it's kind of almost kind of like a back and forth and a back and forth and a back and forth as we go across. Okay, kind of like that in order for us to cut it very well. That's what they're asking for, okay? And it's a special tip. All right, plasma cutting, ma. Okay, so plasma cutting is really super duper cool. It allows you to cut pretty much 90% of the metals out there. That means stainless steel, aluminum, carbon steel, copper, whatever you want, you can do it. Now, the drawback from a torch is what? Well, I can only use ferrous materials or materials that have iron in them. With the plasma cutter, you do not. The drawback from the plasma cutter is I have to have electricity. You know, torch, I can get 2 little bottles for my torch and I can make it portable. So the way a plasma cutter is, what happens is we have a nice little power supply and it becomes DC electrode negative. There's actually an electrode in here, or a cathode, okay? And what we do is we actually energize it. When we energizes it, it creates this plasma arc. In order for it to cut through what we're doing, it actually kind of has this restrictor. And what we're using shop air, compressed air, to help cool it and help push down the plasma arc. Now, this arc comes out at approximately 14,000 degrees. So that means there's a lot of UV, which means make sure you use the appropriate PPE, for this. Okay. All right, so in order to make sure that we have a good cut, we need to make sure that we're using enough power. So we need to make sure, so when we use an orifice, they're talking about the tip size, okay? When we talk about the tip size, this means how tight is the constriction for what we're trying to do, as well as how thick, how fast do I have to do it, or what type of gas do I need? So here we have nitrogen and hydrogen that we're using when it says 100 pounds. So this would be, you got it, shop air. Okay, so that's normally what most people use is shop air. All right, and if we're going to use a mechanized cut, we're going to actually have like a little robot or a little guy that goes on a little track. And we can use this with a plasma cutter, or we can use this with a torch. All right, now we're going to talk about air carbon arc. What air carbon arc is, it allows us, for the most part, most people will use it to gouge out material. Maybe I have a defect in my material that needs to come out. I will be able to gouge it out. Here's the thing, I must also have a stick machine as well as a compressor. Okay, there's a special, I should say, electrode holder that's used in along with your stick machine, and air pressure is connected to it. Okay, usually around the 350 to 400 amp range. So it looks like this. So we have a special electrode. This is a carbon clad electrode, okay? Or I should say carbon clad carbon graphite electrode. Excuse me. Let's try this again. A copper clad carbon graphite electrode, or they just have plain carbon graphite electrodes, okay? And it clips in here, but notice this. These are the little holes that the compressed air will come out, okay? Here's our little release lever. And when you push this button, it turns the compressor on. And what happens is this burns and it will melt whatever we're working on. And the air helps push it and shoot it out. It's really, really cool. It's probably one of my favorites. Okay, so it'll look like this and it'll start to gouge out. So we remember that we need to keep the air under our electrode so it will help scoop the material. So the electrode is melting it and the air is pushing it away. So if we're doing something flat, we want to make sure that the electrode is 90 degrees and we push it. Okay, now if we're going to go vertical, we want to make sure that we go down. What would happen if we went up? Well, if we went up, it would just keep coming down on us. We wouldn't get anywhere and we wouldn't be able to gouge anything out. All right, horizontal. We want to go from left to right. Okay. And of course, beveling. We can make a little bevel on it. Okay. We can also do what's called washing. This is large areas. We can take off pieces, edges, castings, things like that. All right, points to remember. We want to make sure that we have correct oxygen and acetylene pressures because it's dependent on tip size, and tip size is dictated on thickness of material. All right. When we cut cast iron, we want to adjust the preheating flame so it is carburizing. And if we're going to cut non-ferrous metals like aluminum, plasma cutter is a lot more effective. In plasma arc cutting, we set the polarity to DC electrode negative. And when we use air carbon arc, we use plain or copper clad carbon graphite rods. All right, take care, guys.